This video is hypothesis testing with 2 samples. So far, we've completed hypothesis tests where we were testing a sample to determine something about one population. We've dealt with means and proportions. But in this chapter, we will continue to deal with means and proportions, but instead of dealing with one population with one sample, we will deal with 2 populations and 2 samples, 1 sample from each of those populations, and we're going to compare them. So an example would be if you wanted to compare the proportion of voters that voted Democrat in 2 different states. Now, the whole process is pretty much the same as when we learned the basics of hypothesis testing. You are still going to write a null, you're still going to write an alternate statement, you're going to choose which kind of test you're going to run. That's the one thing that's going to be different. We're going to run 3 new tests. Actually, one of them is the same test we've run before. It's just we're going to run it in a different way. But we're going to run 2 sample t-tests. If you go to Stat and Tests, that's number 4. 2 sample t-tests is when we're testing 2 means, 2 population means and comparing them. And then we have number 6, 2 prop z-tests. That's when we're comparing 2 proportions. And then we have something called paired data. That's where you take 2 samples, but those samples are related because maybe it's the same sample, but you're just taking 2 different types of data, like a before and an after type of data. We'll get more into that when we get to those videos, but the test that you would run for that is a t-test, which we've run in the past. We ran that when we were not familiar with what the population standard deviation was and we were testing a mean. So, but again, the 3 tests that we will be running in this section are the 2 sample t-tests for 2 means, 2 prop z-tests for 2 proportions, and t-tests for paired data. Okay, so here are the steps. As I said, everything's pretty much the same. A couple differences. The way we write our null and our alternate hypothesis statements has changed slightly. Now, we're still going to have equal sign for the null. So the difference is, instead of saying the mean equals some number, say the mean is supposed to equal 20 ounces, we're going to assume that there's no difference between the population mean for the first population and the population mean for the second population. So our null will always be mean 1 is equal to mean 2 if we're testing 2 populations to compare their means. If it's 2 populations to compare their proportions, it's P1 equals P2. Both of those are capital. Now, you don't have to use the numbers 1 and 2. Let's say you were comparing the proportion of Democratic voters in Alabama versus the proportion of Democratic voters in Mississippi. You could write P sub A equals P sub M. It's up to you, as long as you know which one is which. Now, your alternate statement will still have an inequality sign. It'll either be less than, greater than, or not equal to. But if you'll notice, there's no numbers here, just like there were no numbers here. It's just notations, just symbols. So mu1 is less than mu2, mu1 is greater than mu2, mu1 is not equal to mu2. Do not replace any of these with numbers. This is exactly how I want you to write it. Now, once we write our statements, then we're going to decide which type of test we're going to run, either a 2 sample t-test, a 2 prop z-test, or a paired t-test. So let's talk about when we're going to do each one. If you have a 2 sample t-test, that is when you are testing 2 population means, and they are independent of one another. They're not paired. And then we have our 2 prop z-test. That's when you're comparing 2 population proportions. And then we have a t-test that we're going to use for paired Okay, now once we do that, we find the p-value just like we found before. We will compare that to the significance level. If it is less than the significance level, we will reject the null. If it's greater than the significance level, we will fail to reject the null. So we make that decision, and then we'll make the conclusion based off of that. And usually, if we reject the null, there's enough evidence to support the claim, and if we fail to reject, there's not enough evidence to support the claim, as long as the claim matches the alternate statement. So let's just go ahead and jump into an example. Example 1, comparing diets. Are low-fat diets or low-carb diets more effective for weight loss? A sample of 77 subjects went on a low-carbohydrate diet for 6 months. At the end of that time, the sample mean weight loss was 4.7 kilograms with a sample standard deviation of 7.16 kilograms. A second sample of 79 subjects went on a low-fat diet. Their sample mean weight loss was 2.6 kilograms with a standard deviation of 5.90 kilograms. Can you conclude that the mean weight loss differs between the two diets? Use a 0.01 level of significance. Okay, so how do I know that this is one of these new kind of tests and not like the ones we did in the previous chapter? Well, we're comparing two types of diets, low fat to low carb, and we took two samples. The first sample was 77 subjects, and the second sample had 79 subjects. So you take two samples, it's either going to be the two sample t-test, the two prop z-test, or the paired t-test. Okay, so we're doing means. Okay, we're concluding that the mean weight loss differs between the two diets. That's what we're trying to conclude. So we're going to do a two sample t-test. And for this one, it's not going to start off with the null, because before with the other types we had to set the null equal to whatever the number was. But in this case, the null is always equal to another symbol, like mu1 equals mu2 or p1 equals p2. So we're going to start with an x bar 1, sx1, and an n1. And we're going to enter all that data in. So our x bar 1 is our sample mean for the first sample. So the sample mean weight loss for the first sample was 4.7 kilograms. And that had a standard deviation of 7.16 kilograms. And that sample size was 77. Then we need an x bar 2, an sx2, and an n2. And our x bar 2 is our second sample mean, which was 2.6. And let's see, 5.90 kilograms was our standard deviation, and there was 79 of those. Now, I just realized that I bypassed writing our null and our alternate statement, so let's go ahead and write those. Now, I could just write mu1 equals mu2, or I could say we're trying to see if low carbohydrate diet differs from the amount of weight loss from a low fat diet. And we want to see if there's a difference. Now, the data that they gave us first, that I put in for x1, sx1, and n1, that was for the low carbohydrate diet. So I'm going to put low carb first as 1 and low fat as 2. So for the alternate statement, I'm going to say the mean of low carb does not differ. Is not the same. Is not the same as the mean of the low fat. You could also do mu1 is not equal to mu2, as long as you know that 1 is low carb and 2 is low fat. Alright, so now we are going to put this in the calculator. So we're going to go to Stat, Test, and we're going to choose 2 sample t-test. There's also a 2 sample z-test, but you would have to know the population standard deviation for both populations, which is highly unlikely. So we're just going to do number 4, 2 sample t-test, because we do not know the population standard deviations for either population. So number 4, And if they give it to you as raw data, we choose data, but they didn't. They gave it as stats, so we leave it as stats. So X bar 1 was 4.7. SX1 was 7.16. N1 was 77. X bar 2 is 2.6. SX2 is 5.90. N2 was 79. Make sure we choose not equal. And we're going to go down and hit, pooled. Where it says pooled, choose no. Choose no for pooled. Always choose no. And then go to calculate. And you see what it gives you? It shows you at the top the alternate statement. It gives you the test stat. And then it gives you the p-value. It gives you degree of freedom. And then it gives you X bar 1, X bar 2, and SX1 and SX2, and N1 and N2. So you can always check to make sure you put the right numbers in if you scroll down. But what we're interested in as far as an answer goes is this p-value, 0.0477. And we used a 0.01 level of significance, and that is definitely greater. So we fail to reject. Fail to reject. And if we fail to reject, we can't reject the null, then we don't have enough evidence to support the claim. So in conclusion, there is not enough evidence to conclude that the mean weight loss differs between the two diets. Okay, so check this one out. Example 2, birth order and IQ. In a study of birth order and intelligence, IQ tests were given to 18 and 19-year-old men to estimate the size of the difference, if any, between the mean IQs of firstborn sons and secondborn sons. The following data for 10 firstborn sons and 10 secondborn sons are consistent with the means and standard deviations reported in the article. It is reasonable to assume that the samples come from populations that are approximately normal, and then they give the sample data, firstborn, secondborn. Can you conclude that there is a difference in the mean IQ between firstborn and secondborn sons? So first, let me just state, this is a two-sample t-test because you're testing two populations and you're comparing their means. But the difference between the last example and this one is they gave us raw data to make sure you're going to put this in L1 for firstborn son, you're going to put secondborn son into L2, and then you were going to run the test, a two-sample t-test, you're going to run it on data. So pause the video and come back, and I will have this worked out for you. Okay, for the null, I put the mean of firstborn is equal to the mean of secondborn, and then for the alternative, because we're trying to conclude that the IQ scores were different from firstborn to secondborn, I put the mean of the firstborn is not equal to the mean of the secondborn. I ran a two-sample t-test and chose data. In L1, I put the firstborn, and L2, I put secondborn. So where it says X list, I put L1, Y list, I put L2. Frequencies of 1 and 2, I put both 1, and then I chose that the mean does not equal mean 2. So I wanted to show you the calculator real quick for that. So I went to stat, enter, put my data in L1 and L2, stat, test, choose number 4, list 1 and list 2 for L1 and I think I put X list, but it's list 1 and list 2. Frequency 1 and frequency 2, choose 1, not equal to, and choose pooled, and then go to calculate. And I got a p-value of 0.8646, which is greater than 0.01, so we fail to reject. That means that we cannot conclude, we cannot conclude that there is a difference in the mean IQ between firstborn and secondborn sons. And I was running out of room, so I just wrote, no, there's not a difference in IQs, but you should really write it out a little bit further. So we'll stop here and pick up with part 2 in the next video.